my camera off?
Yep,
Okay.
that sounds good.
I'm gonna stop my video anyway. I'm gonna sit down in the back.
Sounds good.
Take pictures.
Sounds good. Good afternoon, everyone. Thank you for joining us. We'll get started in a couple of minutes' time. Thanks for coming on nice and early. During the session, you can pop your questions in the Q&A at the bottom of your screen, and we'll answer as many of those as we can at the end of the session. And we are recording it, and we'll share that with you in the very near future. But for now, we'll just give it a couple more minutes and let more people come online, and then we will get started. Thank you.
Right.
Afternoon, everyone. Thank you for joining us. We'll be getting started in about a minute's time, just letting the last few people come online. At the bottom of your screen, you can pop your questions in there at any time, and we'll answer as many of those as we can at the end. And we are recording the session. We'll share that with you in the near future. The time has just ticked over to 12:30, so I'll hand over to Les, who will be your MC for the day. Over to you, Les.
Thank you, Holly. Kia ora, everyone. Welcome to this webinar put on by the Engineering New Zealand Hydropower Group. We're a group of enthusiasts, and if you would like to join the group, then go onto the webpage and join up. We'd be happy to have more members. So today I'm filling in for a few people that couldn't make it, but I'd like to introduce Michael Wachinger of Chesterton. He's the Asia Pacific Senior Regional Manager, and he's based in Melbourne in Australia. So today we're going to, Michael's going to talk about advances in sealing systems for water turbine main shafts. Michael has 16 years experience in mechanical seal design, installation, and applications across various industries. So I'm sure that this is a problem area that people have had on hydro machinery. So I'll hand over to Michael, and thank you very much for presenting today.
Thanks, Les. I really appreciate the opportunity that Engineering New Zealand has provided here, and it's fantastic that so many people have been able to attend. So appreciate the opportunity. So what I'm going to do is run through a couple of slides here, and hopefully there's some good information there that people can have can get some good information about, but also, you know, might tweak some questions, which will towards the end we'll start running through those questions and see if I can answer them as quick as I can. So since the very first hydro turbine was designed and installed, sealing the main shaft has been a significant challenge for turbine designers and operators. Making sure the seal is maintained also causes ongoing maintenance headaches for hydropower plant personnel. Teams need to consider issues such as plant acceptable leakage rates, component wear and component corrosion, cost of cooling water filtration, treatment of leakage water into the turbine pit, and ease of operation and maintenance. Today it's my pleasure to present a few words on the HydroTurbine main shaft sealing, some basic hydro turbine designs and the issues around main shaft sealing in those designs, some history in the seal design, and some of the improvements that have been made over time. Then shall briefly mention the cost of maintaining the current most popular main shaft sealing designs before introducing the latest and what I would call the best available technology, and lastly, citing a reference from Canada. The four most popular hydro turbine designs used around the world are the Francis, Kaplan, Pelton, and Bold type turbines. In 1848, James B. Francis improved on an original Fourneyron and Poncelet French design. And by 1920, the Francis turbine became the most common inward flow reaction turbine design machine in use in hydroturbine stations. It has a high efficiency of water energy to generation energy of greater than 95%. Water flow and speed control are governed by wicket gates or guide vanes. It's best located at the bottom of a penstock or the lowest point of a waterfall. The main shaft seal needs to cope with both axial and radial shaft movements, as well as the penstock head pressure. In 1913, Victor Kaplan created a low head version of the Francis turbine by using an adjustable propeller type blade to harness the water flow energy. Runner blade pitch is hydraulically adjustable to help control the water flow and hence the turbine speed along the wicket gates. It is best suited for low head, high flow applications. The design means that the machine can be mounted at any section of a penstock as long as the draft tube is flooded. However, this can cause vacuum conditions around the main shaft sealing arrangement. In 1870, Lester Allen Pelton expanded on a water wheel concept to create a high head, low flow turbine. Nozzles are used to direct high pressure water into the cups, which are called impulse blades, which are mounted on the OD of a drive wheel, which is also called a runner. This causes the wheel to rotate. High efficiency can be achieved with high pressure but low flow applications. The turning shaft may need two seals because potentially the direction of the installation will determine whether there's water being applied on both the lower and the upper seal arrangement or between the left and right if it's mounted on a vertical arrangement. The bulb turbine is basically a Kaplan turbine with the generator housing inside a giant bulb with a horizontal axis propeller design placed in the water flow. It's good for low head applications and high efficiency can be achieved with little water capacity applications. The main shaft seals here are often difficult to access. When water turbines were first developed, labyrinth seals were used primarily on low head pressure, smaller shaft diameter applications. The labyrinth created a tortuous path for the liquid to escape through a number of vanes passing through housings, which effectively created small pressure points, which would then be tended to be higher than the vane below it, and hence reduce the pressure, the speed of the escaping liquid through the maze. However, as shafts grew and penstocks heights grew, compression packing was then often used to seal the main shafts. Packing offered adjustability for leakage control with the opportunity to renew the packing from time to time as required. Packing works by compressing the material axially in order for it to seal against a stuffing box bore and the turbine shaft radially. The more you squeeze or compress the packing, the harder it would seal against these two elements. And so in theory, the lower the leakage rate would become. However, the higher the wear rate, specifically on the shaft sleeve, would also become. Therefore, early packing designs require a significant amount of water to keep it cool and from the friction generated by the turning shaft. Using the supply water as cooling lubricant for packing meant that often abrasive materials from the river or the dam became embedded in the packing and accelerated the wear of the main shaft sleeve. As clean as possible, flushing water is used to not only help with lubrication, but to keep the particulate material from contaminating the packing and the sleeve. As the packing wears down, it requires periodic adjustment to limit the amount of leakage. However, oftentimes this leakage would cause the station's drainage system to become overwhelmed. This could result in water contamination of other turbine components, including all lubricated bearings, as well as overall flooding of the station. One advantage that the gland or mechanical packing has that it tends to support the shaft that it is sealing against. Therefore, axial or run-out movements can somewhat be tolerated. Then came along segmented bushings or plates. These were originally made using metal-to-metal surfaces, a softer metal such as a bronze against a harder metal such as a stainless steel, with lots of cooling or flushing liquid required. Eventually, the softer material was replaced by carbons or derivatives of carbons, and these segments were then these segments were introduced to greatly reduce the friction and therefore the amount of flushing water required. For ease of installation and to assist in cooling water flow, the carbon and their metal segments are made with overlaps held together with garter springs, particularly for radial seal designs, or metallic holders, particularly in axial seal designs. However, due to carbon being a softer material, the seal can wear out rather quickly. More recently, the high-wearing carbon segments have been replaced by elastic polymers and polyurethanes with machine grooving to assist in the cooling flows. These materials are hard-wearing, yet still provide good sealing in many conditions, but are still segmented and held together in position by the same traditional methods as earlier stated. Cleaning, flushing water is still required to maintain abrasive-free cooling lubrication in this design. So again, leakage into the turbine pit area can be sometimes significant. As compression packing technologies have evolved, fewer materials or newer materials and lubrications with blocking agents have been developed to reduce the amount of cooling water required to maintain acceptable packing life. These are also designed to handle particulate contamination. Now there are things called an automated gland adjustment systems, which utilize pressure feedback to assert more compression loading as packing material wears out. And that's been just recently introduced. Using plant compressed air, pneumatic cylinders push floating gland followers further into the stuffing box, improving the sealing capability of the packing material. So in many cases, the combination of newer compression packing with automated gland adjustment systems can be a cost-effective and effective solution. This solution also allows operators to maintain a reasonable controlled leakage rate and improved lifespan as positive outcomes. And yet, all of these sealing technologies, the cost to maintain, this to service and to operate continue to be somewhat of a burden. Often the main shaft seal is difficult to get to, making adjustments and repairs difficult in these tight space constraints. Most systems today still need a clean as possible flush water system for cooling and lubrication, which can lead to many additional burdens such as what to do with the leakage water, as it needs to be treated before it's released back into the environment, as it also collects oils and greases from bearings and associated equipment on its way down to the turbine pit. Then there is the corrosion issues, as the leakage water touches many other parts of the plant. And what if that water gets into the all lubricated main shaft bearings? Then that leads to even more failures with water washout and corrosion along babbitt or white metal bearing surfaces. Add to this the complexity of seal design changes and having to do the repairs and the changes themselves. Most of today's technology have many moving parts, which are designed to be small for ease of handling and in tight locations, but also mean that there are a lot of moving parts, and these need to be put together to make sure that the seal works properly. And then there is the clean as possible flush water. Most systems involve filters and pressure pumps with associated controls and preventative maintenance programs. Backwashing filters or simple replacement means added costs and added treatment requirements. Many of you would recognize these types of systems in your own plants and know the importance of ensuring that these remain running well. However, today with advances in sealing materials and designs, axial shaft seals have now been developed to provide excellent sealing capabilities with minimal and in some circumstances, no leakage of lubrication with cooling liquid. These designs are also, in the main cases, do away with the cleanest possible flush water systems, instead using the feed water directly from the penstock to act as a lubricant. This is made possible by using silicon carbides as face materials, which are extremely hard, therefore able to withstand abrasive sediments present in the water, and then designed with surface geometries that allow a balance between leakage and wear rates, allowing the seals to vaporize the feed water into a mist along the atmospheric side of the seal surfaces. I won't go into the exact science behind this, but feel free to contact me later on if you'd like further explanation on how this works. Because seal face designs are actually assembled, the rotor element cannot score the main shaft sleeve, and due to its wide face design, allows for larger radial movement, which can be common in turbine shaft runouts, particularly when the equipment has been running for many hours. Then with long finger springs, actual movements such as hydraulic lift can be compensated for, allowing sealing to be maintained throughout the various hydrodynamic effects during running, and particularly with startup or slow running processes. Another great advancement is the use of a ball and socket O-ring. These designs make assembly around a shaft very easy. There's no need for glues or sealants, as the two halves are easily pushed together and click into position. Hydraulic forces surrounding the O-ring ball and socket joint tend to force the halves together, creating an even tighter seal. Typically, when it comes to reducing leakage rates, you sacrifice longevity, since the seal components are forced solidly together to create a strong seal, which means that friction between the rotating and stationary components increases, and hence they, or at least one of the halves, wear out quickly. However, with seal face balance learnt from various mechanical seal applications over the years, larger size designs have now been applied to many HydroTurbine main shafts for sealing purposes with good success. To date, many hundreds of these types of seals, ranging from 150mm shaft size up to 860mm, have been running between 10 to 20 years of service, with an estimated average in our case, in Chesterton HydroTurbine seals case, of roughly 15.4 years service life without breaking down or repair, with minimal need for flushing systems. Also, the designs are capable to be split in two, which means 4 pieces Also, these designs are able to be split into 2 and sometimes 4 pieces for ease of handling and installation. So with increased uptake of new technology, not only by end users, but also by HydroTurbine OEMs such as Andritz in Europe, for installations all around the world, the growth of this technology continues. The benefits of ease of installation, minimal leakage, minimal and in many instances no clean as possible flush water requirement, together with predictable life due to worldwide experiences and visual or electrical wear indications, make this latest technology a viable option for both retrofitting to older equipment, but also for new designs and installations. To provide a case study reference, I've included the remaining slides to AltaGas HydroTurbine power sites in Canada. AltaGas is one of the larger energy producers supplying the Canadian people with gas and hydroturbine powered electricity. There are 3 hydropower stations located in the remote northwest of the country, generating approximately 280 megawatts of power for the grid. These stations are the Forest Kerr, the McLearmont, and the Volcano Creek, and construction began in 2010. The original main shaft seal was a split segmented polymer design which leaked profusely upon startup and even when controlled, still used huge amounts of flush water. Many times these segments would break, causing unplanned downtime and long hours of sealing rebuilds. In 2017, the first axial split mechanical seal was supplied to Unit 7 at the Forest Kerr. The clean flush water flow was cut down to 1/8 of its original supply initially and gradually reduced to a trickle as the mechanical seal obtains its lubrication from the river water. With successes on Unit 7, eventually all 9 units at Forest Kerr were converted over to a mechanical split seal design with the same result. No leakage at startup or during running and minimal flush requirement. With the success of Forest Kerr, all 3 at McLearmont were retrofitted with a similar design mechanical seal, again for the same result. No leakage at startup or during running and minimal flush requirement. And then finally, all 3 Volcano Creek plants turbines were converted over to a mechanical split seal design. All of these sites installations have been running trouble-free to date with no discernible leakage. Recently, an experiment had been undertaken to completely eliminate the clean flush water, as the river water is considered clean enough to provide seal face lubrication. The cleanest possible flush system will remain on standby, but so far things are looking good. Matt Webber is the plant manager responsible for all 3 sites at AltaGas, and he sent us this lovely note, which I'll just give you a moment to read. If you wish to have Matt Webber's email address, he's more than happy to talk to anybody about his installations. So thank you for listening to this History of Main Shaft Sealing webinar. And I hope that I've shown that what some of the latest or best available technology can do to help improve the maintenance and operations of your turbine. There is a QR code down the bottom here on the right that you can use to scan or download this an entire white paper around this topic, and it covers it in more detail. So feel free to grab that at any time. But Les, I understand we might be open the floor to questions.
Yes, absolutely. Thank you, Michael. That was a great presentation. So has anybody got any questions? I haven't seen anything come up on the Q&A at the moment. How about I just ask a question just to get people going, because we have a few minutes left. So Michael, in New Zealand, we do have a bit of dirty water in places. So we have volcanic ash and things like that in our water. How do these seal arrangements cope with that sort of solids in the liquid?
Yeah, that's a good question. So certainly our experience is showing that issues such as packing, for instance, will require significant amount of clean flush water in order to ensure that the packing stays in a trouble-free environment, to keep the pressure up around the packing arrangement, and also segmented bushes as well, to ensure that none of those solids get mashed up between the sealing arrangement and the main shaft seal or the sleeve itself, because that obviously causes issues. With mechanical seals, there is a certain level of solids that they can cope with. If you to run a mechanical seal on, I guess we call it a slurry situation, basically, because the water has got solids in it. And in a slurry situation, it depends on the type of slurry that you're using. So the solid that comes out of the dam water, what shape is it? How hard is it? What sort of content of it? Like by percentage by volume, for instance. that will all determine on what the design of the seal needs to cope with, but also how much additional or lack of additional lubrication is required. So just to throw some numbers at you then, you could probably run up to 40% of solids in your water without the requirement of an external flush. So 40% is quite a lot, but that would also depend on the type of solids that they are. You know, how hard they are, like I said, what shape they're in, those they prefer, etc. You know, we see a lot of applications, you know, even that one in Canada, while in summer it's a lovely situation, but in winter where you get the ice turns up and then it starts to melt in spring, and with it comes half a tree or 10,000 leaves and lots of rocks and all sorts of stuff come with it along the way. So we find that increase in solids through that period of time gets to the point where it's possibly just on that 40% mark. And so the seal can cope with it quite nicely. But, you know, when you start to see a little bit more leakage come through the seal, it's supposed to evaporate basically. But if you do see some drops coming through, then it's a matter of turning on that bypass or that clean flush water to be able to clean that section out. There's also new technology involved where you can extrapolate solids away from the seal faces area by using a certain design bush in that segment as well. So it's kind of isolating the I guess I'll call it the seal chamber area or the stuffing box area of the main shaft seal there. And there's a way of reducing the solids out of that using some new technology. So it's a good question.
Okay, great. We have got a few more questions come through. So thank you, people. We've got a question here from Hussein. What would be the minimum flow rate? I'm not sure if we're talking about the flushing or leakage.
Yeah, you see, so the minimum flow rate, generally when you talk about a mechanical seal, in order to ensure it's going to run properly, you need some liquid around it. Now, generally what we say is you have some sort of flush go past the seal at a certain flow rate, and that is dictated by the seal face geometry, but also by the size of the shaft that it has to seal on. So the larger the shafts, generally, the more flush it's required to be able to maintain cooling and to remove solids, etc., from the seal face. So what we've found though is in many applications, if we dead end the stuffing box area and therefore dead end the seal, the generation of heat is so low that the surrounding metallic components are able to absorb that heat, which means we don't need as much cooling, therefore we don't need as much flow rate. So, you know, it's hard to put a number on it. Talking like a politician now, but generally, yeah, the larger the seal, the more flush you generally need. But as I said, so what we've been able to do is reduce the point of the flush requirement by having a dead-ended system or having a system that extrapolates solids away from the seal faces, as I mentioned before. So yeah, so it's, like I said, hard to put a number on it, but if you were to provide your application details, you know, we can certainly do some calculations around what our expected flush rates would be or flow rates would be.
Great, thanks. So we've got another question here from Alex. He's referring to the RPM consideration. So what maximum RPMs are feasible for the seals that you'll?
Yeah, so our experience so far, and we've probably got about 150 to 250 mechanical seals out there in the HydroTurbine applications around the world. Our fastest one is probably around the 900 RPM mark, thereabouts. But generally we find the larger seals are down at 400 to 500 RPM. So we can cope with that sort of size. And Alex is right, because at the end of the day, you've got what's called a PV value, which is a pressure velocity value. It's a very important point in how you maintain the seal arrangement between the stationary and the rotating seal faces. So to have to understand not only the pressure from the headstock, but also the speed of rotation is extremely important to analyze that. In fact, the white paper goes into a little bit more detail around that, around the PV areas and how important that is. But yeah, generally, yeah, we've got 960 RPMs, I think, from memory, but they're generally the larger ones are down at that 500 RPM sort of mark.
Okay, thanks. Another question about what is the expected life of a seal, the run hours?
Yeah, so that's a very good point. Mechanical seals in particular, they have one seal face is designed to wear. It's part of the design, conditions, etc. Now the wear rate of that all depends on lots of things with respect to the PV, for instance, but also, as I mentioned before, also movements in the shaft, upset conditions, solids in the system, etc. All those things play a part in the wear rate. During my presentation, I mentioned that certainly from Chesterton's experience anyway, that the main shaft turbine seals that we have out there at the moment, we're averaging around 15.4 years life of the wearable seal face. So, that's basically an average of those 150 to 250 odd designs that are out there at the moment. So maybe that answers the question. But, like I said, if you've got a really troublesome situation or you've got a shaft with a heap of run out or even actual movement, etc., that's obviously going to cause a problem. We would need to really understand the application to design the seal around that specifically. As far as packing is concerned, though, or even segmented bushes, they're a lot smaller, a lot quicker, I should say. They should wear out a lot quicker. Segmented bushes and the new polymer ones last longer. The carbon ones will run out a lot faster, and that's again to do with the PV and the rotating speed, in particular around the V side of the PV calculation. But yeah, packing would last probably, I don't know, somewhere between 5 to 10 years, depending on, again, the friction and the amount of leakage rate that's acceptable by the plant. So therefore that dictates the compression, therefore, the friction increases, therefore the wear out is quicker. So yeah, it's a combination. The questions are not so easy to answer, of course, again, being a politics person, but yeah, it's always a balance between the leakage rate and the shaft friction and therefore the wear rate.
Great. Well done. You could be a politician, I think. So we got another question here to please explain the spiral track and how that extends the seal life. So maybe a bit more explanation on that.
Yeah, so I mentioned before about, in one of the earlier questions, about if you could extrapolate the solids away from the seal faces, and whether that's packing or whether that's segmented bushing, by isolating the seal chamber or the stuffing box area by using a bush. Now, the bush is the type of bush that you use in that area is very important, because not only it needs to have a close tolerance to the rotating shaft, but in the spiral track, which is a trade name for a particular product that is used to remove solids out of a stuffing box. It has a groove cut inside, or multiple grooves that spiral away from the seal chamber. So the concept being that the turning shaft has a momentum or a centrifugal force that pushes solids materials that are inside the liquid out away from the shaft. What happens is, as it gets pushed out and it hits those grooves in the bush, then the rotating movement not only provides that centrifugal outward force, but also allows the materials, or the solid materials, to move their way down the spiral and back out of the seal chamber. So what you'll find in a vertical situation is that when you first flood the chamber before you start turning it on, and when I say chamber, I'm talking about the seal chamber around or the stuffing box area, then solids can get in there quite easily because they go through the gap between the shaft and the bush itself, fall into that seal chamber area, excuse me. But as the shaft starts to turn, the centrifugal forces pushes those solids out into the groove area, and the groove then pushes them back out of the process and back into the standard flow of the liquid and away from the seal faces. So spiral track is a trade name for that particular type of bush. It's a type of bush that has a spiral cut inside there, and it's a very effective design in removing solids out of your seal chamber or your stuffing box.
Great. Paul's got another good question. It looks like it's a lot of positives, but what are the downsides? What applications are perhaps not suitable for this type of seal?
Yeah, so again, it depends. If your station mandates that you have to use flush, okay, that's great. That's going to make the seal last longer, but that's also going to add cost. Now, if we were to come back and say, okay, let's delete the flush, but if it turns out that the solids are, I don't know, 60% of the water, or they're millimeters in diameter, or they could be, it could be rocks that you're trying to pump through. These are the sort of things that will dictate the life and therefore the design point. And we'll quite clearly say that if your shaft is let's say 1,000 millimeter diameter and it's running at 2,000 RPM, I don't think I'll be able to design a seal that's going to fit that properly. Certainly not a mechanical seal. So look, there are constraints around what we can and can't do. And at this point of time, we've been able to achieve a lot of good results based on selecting the specific applications. So I think that's a thing. And I'll be perfectly honest, the other downside, I suppose, if you want to call it, or the negative, is it's expensive design. Mechanical seals can be very expensive, especially the way that they're designed for the application. Certainly a lot more expensive than standard packing, and probably a little bit more expensive than a normal axial seal or a carbon type of bushing seal. Probably on par with your segmented polymer seals, probably similar to that, maybe a little bit more expensive. So so your return on investment has to be very strong. We have to understand, what are we trying to save, how long can the seal last, etc. So that's probably a downside. And like I said, I'm just being honest.
Great. There's a couple of questions about the Chesterton 442 mechanical seal and its repair, and are there repair kits available, and is it expensive and that sort of thing?
Yeah, so the 442 is our, I guess it's our name that we use for a split seal, a split mechanical seal. The main shaft turbine seals that I demonstrated earlier on are based around the 442 design. And so just for those that don't know, so that's what 442 means. So yes, of course, anytime you design any sealing arrangement, the ability for it to be repaired has to be taken into consideration. Any upsets that do occur that cause a problem with the seal or what have you, and you'd have to replace the components. Seal kits are available, repair kits are available. The beauty about the seal design that I showed earlier is that very few parts are involved, and so therefore having a kit that can be brought in on site and a repair undertaken locally and very quickly is very possible. In many instances, we can turn around a repair probably in a few hours, maybe a day at the most. So, they're all those sort of things that keep taken into consideration with the design. Great.
Going back to the solids and the liquid, there's a question here about 40% pumice particles. Would that be acceptable as an instance?
Yeah, so again, I don't want to commit 100%, I'll be a politician here. I'd love to see some more detail around the actual specification of the liquid. So, what the content looks like, or what that solid looks like. 40% is an arbitrary number that we've used for many years now as far as the design of the seal faces are concerned. So we know that we can cope with generally 40% of most solids. But again, we'd like to be able to look at the closer detail around what that seal looks like, sorry, what that solid looks like and in that particular application before I comment any further. But certainly, yeah, happy to do that. If that person can, you know, send us an email and let us know for more details, I'll be happy to go through that.
So now we have a question about a ballpark figure in US dollars for a 300mm diameter seal running at 428 RPM at 1.5 bar under the head cover, under the head cover. So there you go. There's a specific one. See how you can tackle that.
All right. Yeah. So, you know, again, the political answer is it depends. It depends. You know, I could say that we always work on ROIs, return on investment. So if you currently use something that you need to replace all the time, the cost of that replacement, the cost of downtime while you do that replacement, the cost of the flushing requirement that you currently use, not only just the process of keeping that liquid clean as possible through the filtration purposes and what have you, but also the flooding that happens and what happens to that liquid as it leaks through. How do you process that? All those costs are involved. You know, that becomes a big number. And then you come up and say, okay, mechanical seal, 300mm, 400 RPM, that's not too bad. I think we could probably cope with that one. Somewhere between Australian dollars, sorry, I'll start again, US dollars, maybe between 50 and 100,000. It depends on, again, depends on what we're trying to achieve. If you're going to allow lots of flush and you're happy for the flush water to go through and you don't want to turn your flush off, we can modify the design of the seal to allow, maybe it's not as superbly manufactured, if you want to call it that. It's probably not the right word to use, but you know, there are certain features that we wouldn't need on the seal faces in order for them to cope with a flushless situation if you've got a flush, in which case we can reduce the costs. But, you know, sort of, I don't know, that's I guess a political answer for you. It depends.
Yeah, that's great. So do we have any seals, the seals as you've been describing, the new seals in New Zealand at the moment that you're aware of?
Yeah, there are one or two around at the moment. I know that we've been involved with 2 or 3 installations in particular, but they could have been the same seal. But yes, there are a couple through, and I don't want to specifically talk about who they're for, but certainly if you wish to ask some more questions, then I'm sure I can head you in the right direction of where to find out who's running them and how well they're running. But yes, we have a couple of installations in New Zealand already.
Okay, and we've got another question about when water freezes and becomes ice at startup. So do we have any effects there? Is that something you've come across?
That's an interesting one. Yep. So right. So if I put my design hat on, as you know, as you start to turn the shaft, depending on how big the shaft is, of course, your PV number is starting to increase. So as the velocity starts to turn, you're going to create friction between the 2 face materials. That friction creates heat. The heat, in theory, should melt the solid ice around there and therefore allow the lubrication to occur. Now, having said that, it would depend on the speed, it would depend on the shaft size diameter, of course. It would also depend on the ability of the ice to melt. In other words, how cold is it? Is there anything in the liquid that is going to cause it to change its state from the solid to the liquid with respect to what temperatures, what pressures are involved? There's a lot of questions around that. But yes, in theory, if you had ice and it stayed ice for a long, long time and it took a heap of temperature, a blowtorch to melt the ice, then you're going to have a shortened seal life because it means it's running dry. You need the liquid to lubricate between the 2 seal faces. So solid ice is going to cause a problem. But again, depending on how solid that is, and how quickly the friction generated heat melts the surrounding water to be able to feed the seals, will then to give us a much better idea about the life of the seal. It'll still seal, but it'll just reduce the life, because if you've got startup issues like that, then yeah, that's something we need to consider.
Great. So we had another comment here about, or a question of whether you have a questionnaire sheet that you could fill out to see, you know, which equipment is suitable for people's applications.
Sure.
Is that something you do?
Yeah, we could do that. Yeah, that's pretty simple. I think my suggestion would be, if you were to download the QR code on the screen here, then when you ask for the white paper, you can put in a comment, or you can put your name and address details, etc., in there. Then and if you wish to ask for certainly a form guide or a request for quotation form, etc., then yeah, we can throw that in as part of the email response to you. So yes, there is one available, and it goes through all of the standard type of questions that are required for us to have a better idea about the design.
So another question here about how new is that new sealed axial split seal design? Is it something very new, or?
Yeah, that's a good question. So Chesterton started the split seal type arrangement in HydroTurbines probably back in 2005, I'd say 2005. Since then, we have selected customers that, for instance, that one from Canada, where we were being pestered to come up with a help, because they were in so much debacle up there. They wanted some help. So it took us a while. It took us up to, I think I mentioned 2017 was the first seal design that was installed in Canada. But up until that point, we had installations in China and in Europe in particular. And so they have already been proven out, and they're still running, which is nice. I've got quite a few in Indonesia that's still running really well. So how new is new? The first design probably 2005-ish, thereabouts. And every year we come up with some new technology around the type of seal face geometry that is best required for each application, and we're starting to get the runs on the board for that. So 2005, so yep. However many years that is.
Right. So Lyle's just made a statement that in Indonesia they've had 3 hydro turbines with MS 442 seals in them, and they've had no issues so far. So that sounds good, and you're probably aware of those installations.
Yeah, that's right. They're 300 millimeters too, those ones, if they're the ones I'm thinking of anyway. So yeah, look, we're a great team up there that does a really good installation, and that's obviously a key point, is to ensure that the installation is done right. I've got a good team in New Zealand too, by the way. So yeah, great methodology. Some people know what they're doing. They've done it before. They've they take care. They follow the instructions. All that sort of stuff. It's important to get it right, to get the setup right, for it to last long and for it to not leak at all. So you're relying on that as well. That's part of the process. And Chesterton does a great job of training plant personnel as well. So if your viewers here want to get more training or more understanding about how these things work and why it works and what are the important things to look out for and how to do your own repairs or what have you, then certainly we can cope with that. But we do have people on the ground in various countries that can help out that, and they're fully trained by us and do a really good job for us too.
Great. So I'll just the last one here, and then we'll wrap up. So we can expect no leakage from the seal and no wear from the shaft. Is that where we're heading?
That's what we're hoping for. Exactly right. Certainly no wear on the shaft. No wear on the shaft is we can already get that, right? So that's a simple one. We can fix that one straight away. The no leakage rate, that depends again on each application. That depends on the size of the shaft and the speed, the conditions of the water, etc. Acceptability of the plant. There's so many inputs into that no leakage rate. And like I said, all mechanical seals will leak. So they will leak in a vapor sort of situation. So you won't see it. You won't see the liquid vaporizing out. It just goes into the atmosphere. So from that perspective, yeah, no leakage is possible. And that's what we're trying to drive to. But really it's no shaft wear, that's true. But we want the seal to last as long as possible. So ideally, between shutdown to shutdown. And, you know, if you think about what are the reasons why we do shut down a plant, you know, it's bearing life. You know, the Babbitt bearing can only handle so much. The white metal bearings need to change. You know, Les, you're the electrician guy here, so even the generator probably needs to be shut down occasionally for refurbishment, etc. So each one of these shutdowns, we want to plan them. We want to understand what's required. You know, we've got a budget for it. All that sort of thing needs to happen. We do it the right season. So if we can have the main shaft seal last between those shutdowns, then that's a really good step. And then the next step is, can we make it last between 3, 4, 5 shutdowns, you know, so that you're not having to replace components along the way. That would also be a fantastic end goal. So yeah, to answer the question, shaft sleeves and shaft wear, we can fix that straight away. But leakage rate and the wearing out of the mechanical seal itself or the sealing arrangement, that's up to the application, and we're doing a reasonable job at the moment.
All right, well, yeah, that sounds really great, Michael. I must admit, for an electrical person, I learned quite a bit about mechanical seals, which has always just stayed well and truly away. So no, that's really great, and great to see the technology improving. Obviously, from an asset management point of view, that's really important for our plant, and you know, we want to keep the reliability up and keep the machinery running, but we know that there's maintenance on this type of equipment. But it's certainly the technology is helping, and some great advances. So really appreciate you giving us some insights, and would really like to thank you for giving your time and your presentation. And please, everyone, if you have any more questions, get hold of Michael, and I'm sure we're going to have some follow-up information coming back out to you. So you know, please make contact, and if you see another webinar come up from the Hydropower group, just jump on, and hopefully we'll have some interesting topics for you in the future.
Fantastic. Thank you again, Les. I really appreciate the opportunity to present today, and I hope people will get an understanding about the latest technology that's out there, and that, you know, we're constantly looking at improving. So happy to field any questions that you have. But thanks again, Les. I appreciate the opportunity.
No problem. Thank you, everybody, and I'll let you get on with your day. Thanks, everyone.
Bye.